Good afternoon, everyone. Thanks for staying in the last session. My topic is about privacy-preserving centralized dynamic spectrum access system. This is a joint work with Kexiong He, Professor Yalin Yang, who is my advisor, Bo Chaowen, Professor Kui Ren, and Professor Shaoqian Li. I'll start with some background. As we all know, dynamic spectrum access, DSA, is a crucial solution to mitigate the spectrum scarcity problem. The basic idea of DSA is to reuse the spectrum holes in the dimensions of power, frequency, and time. One key form of DSA is federal commercial spectrum sharing, which means that governments are willing to share their federal spectrums with the commercial industry players. This form has been recommended by P2-SAS to realize the full potential of government-held spectrum to spur the economic growth. P2-SAS and FCC also recommended to use a central system called SAS to govern the spectrum sharing. The system model of SAS involves three parties, including incumbent users IU, secondary users SU, and a SAS server. SAS server needs IU and SUs to share their operation data to perform the spectrum allocation computation. But this brings about new challenge, which is the privacy of IUs and SUs. IU's operation information is often classified data. For example, in 3.5 gigahertz band, the IUs include military radar and fixed satellite licensees. SU's operation information may also be commercial secret. For example, it is highly likely that SU network operators are reluctant to share their base stations deployment and configuration strategy. But in the current SAS proposal, both IUs and SUs need to share their operation data. This would expose IUs and SUs to potentially severe privacy violence because SAS is not necessarily trustworthy for holding such sensitive information. According to P2-SAS and FCC, SAS may be operated by some commercial third parties to enhance its efficiency and scalability. To respond to this call, Google had built its third generation of SAS framework. Even if we take a step back and assume that SAS is trusted, it may be breached by attackers from inside and outside. Because there is so much sensitive user data stored in SAS, there is a big incentive for attackers to compromise it. And once it is compromised, all the sensitive user data would be obtained and exploited by attackers. So we don't want this single point of vulnerability exist. Therefore, we would like to ask a question: whether it is possible to build a system that can provide the service and preserve users' privacy at the same time. The answer is yes. In this work, we propose P2-SAS to achieve both goals. The basic idea of P2-SAS is that users can encrypt their operation data before sharing with SAS, and then SAS can perform the spectrum allocation computation on the encrypted data based on some fancy properties of some crypto primitives. So in the following presentation, I will first introduce these crypto primitives about how we compute on encrypted data. And then I will talk about how we secure SAS process by using the crypto primitive. And then I will talk about some tuning and acceleration method to refine the system. And finally, I will give the performance evaluation result. So the crypto primitive that we use in this work is called homomorphic encryption. Homomorphic encryption is an encryption scheme that allows computation on ciphertext. It consists of 3 functions. The first 2 functions is nothing special, and they are contained in all the public key crypto system. For the encryption function, given a message M and public key, it can compute a ciphertext C. And for the decryption function, given the ciphertext C and the secret key, it can compute the original message M. What we are more interested in is actually the third function, which is the evaluation function. The evaluation function can be parameterized by a function f, which can be additions, multiplications, and so forth. The evaluation function takes 2 ciphertexts as input, C1, which is the encryption of M1, C2, which is the encryption of M2, and it output a new ciphertext, C3. What is interesting here is that when we decrypt C3, we can actually find that it is equals to f of M1 and M2. So for example, assume f is addition. So we can encrypt 2 numbers, let's say A and B. And after we apply the evaluation function, we can actually get the encryption of A plus B. When we decrypt it, we can get A plus B. So the crypto primitive that we use in this work is a Pilot crypto system, which supports additions, scalar multiplications, and the subtraction on the ciphertext. The scalar multiplication means that the product of ciphertext and some fixed constant. So next, I will talk about how we secure the SAS process by using the properties of Pilot crypto system. The typical scenario of P2-SAS includes a SAS server, some IUs, some SUs, and a K distributor. The K distributor generates a group pair K pair and distribute the public keys to all the parties. Each SU also generates its own pair K pair and distribute the public key to SAS server and the K distributor. So the P2-SAS works as follows. In the initialization step, the IUs generate its operation data, encrypted by the public key, and send it to SAS server. When an SU, let's say SUB, wants to access the spectrum, it also needs to generate its operation data, encrypt it, and send it to SAS server. SAS server would perform the interference calculation securely to work out an intermediate result, which indicate whether SUB's operation will cause harmful interference to any IU. This intermediate result would be sent to K distributor for K conversion service. And later, SAS server would compute a certificate that is generated by SUB's public key and send it to SUB. So only SUB can decrypt it and find out the content of the certificate. So as we can see from the previous slide, the main computation task of SAS server is interference calculation. To do interference calculation, we need some radio propagation model. So in this work, we use the highly sophisticated long-derive model, which takes 13 input parameters. Because secure computation is very expensive, we need to identify the privacy-related input data and do the secure And if we can do the secure computation only on this privacy-related data, and the remaining public data is done in the plaintext form, we can greatly reduce the computation overhead. So the private input data is summarized in this table, including IU, SU location, antenna height, operating frequency, IU's interference threshold, and SU transmit power. We have notation for each parameter. To further reduce the computation overhead, we quantize the location, antenna height, and the operating frequency into discrete values. IU's input TI would be a three-dimensional matrix. So if IUI is in location L with antenna height HI and operating frequency Fi, the corresponding entry in this matrix would be sent to this IU's interference threshold, and all the remaining entries will be sent to 0. Similarly, SUB's input is also a three-dimensional matrix. The entry that corresponds to SUB's operation position, J, HS, FS, would be sent to this SUB's transmit power, and all the rest entries would be sent to 0, indicating that there is no active transmission in these operation positions. SAS server maintains an interference map I. An entry in I hold the attenuation value from one SU location to one IU location. So next, we try to disintegrate SAS process into some basic operations. First, SAS server needs to create an interference budget matrix, which indicates the interference budget in each IU operation position. SAS server first needs to aggregate all the IU's input by summing them up and then converting the 0 entries to infinite, which indicates that there is infinite interference threshold in these operation positions where no IU exists. Next, SAS server makes spectrum allocation decision based on SU operation RB and N. First, SAS server needs to compute the interference FB from the SUB to all the IU operation positions. And then SAS server needs to subtract the interference budget by the interference caused by SUB. So if there exists an entry in this GB matrix that is smaller than 0, that means that the SUB's operation will cause harmful interference to an IU because this IU's interference threshold is exceeded. So this SU should be denied to access the spectrum. Otherwise, SU should be approved to access the spectrum, and the SAS server needs to generate a certificate to this SUB and finally update the interference budget matrix by subtracting the interference of SUB. So this slide summarizes the computation of SAS process. The operations in the green box are all composed of additions, scalar multiplications, and subtraction, which are all supported by the pilot crypto system. So we can securely compute them by converting them from to the ciphertext domain. But we do have some tricky parts here. The first one is the secure integer comparison problem, because we need to compare the value of t prime with 0 securely. Secure integer comparison problem is a hard problem And the existing method to solve it all needs the data to be bitwise encrypted. But bitwise encryption would make the remaining part of SAS process extremely complex and time-consuming. So it is not applicable here. The second one is also a secure integer comparison problem. And the third one is a secure digital signature generation problem, because a certificate needs to contain the information that whether SUB is allowed to use the spectrum or not, and the allowable operation parameters. This information is all encrypted, and still we need to create a digital signature on it, because we need to prevent forgery attempts. But no existing method provides solution for this secure digital signature generation problem. Due to the limited time, I will not cover the details of how we solve this problem. But basically, for the first one, we use a clever way of integer encoding to circumvent this secure integer comparison problem. And still, we can get the comparison result securely. And for the second one, we take advantage of the key conversion service without adding much extra overhead. And for the third one, we leverage radio operations of double nature plus digital signatures integrity property. So with this method, we can generate digital signatures securely without revealing the information like whether SU is allowed to operate or its allowable operation parameters. So next, I will talk about some tuning and acceleration method to refine the system. Recall that we have quantized some parameters. Quantization introduces quantization error, which would lead to either interference underestimation and interference overestimation. Interference underestimation should be strictly forbidden because it would cause the accumulated interference on an IU exceed its interference threshold. So we prevent this by quantizing the parameters to the humble direction so that we never underestimate interference. The interference overestimation would cause underutilization of spectrum, which is undesirable yet tolerable. So there is a trade-off between interference overestimation error and the computation overhead. We quantitatively started this trade-off by this optimization problem. By solving this problem, we can get the optimal quantization granularity to minimize the interference overestimation error when the computation overhead is bounded. We also introduced some acceleration method to further increase P2-SAS efficiency. The first one is factoring. As we can see from this factoring equation, from the left side to the right side, we can reduce the number of homomorphic scalar multiplication from k to 1, while the homomorphic additions is kept the same. So we apply this observation to all the possible places to reduce the number of scalar multiplications. And we also pre-compute some computationally intensive part. The third acceleration method is ciphertext packing. We pack multiple integers in one ciphertext so that these integers can be homomorphically operated at the same time in order to increase the throughput. And the last one is parallelization. We distribute the computation task to multiple threads on multiple servers. So finally, I will give the performance evaluation. We implement a paleo crypto system by setting the security parameter into 2048 bit so that we can have one 12-bit security level. And we distribute the computation task of P2-SAS to 24 threads on 3 desktops. We evaluate P2-SAS on Washington, D.C. area. The first thing that we are interested in is accuracy. We want to measure the error rates of spectrum allocation decisions compared with traditional SAS implementation. The traditional SAS implementation does not provide any privacy-preserving features and it does not do quantization. We focus on false positives and false negatives. False positives refers to the scenario that an SU should be denied but eventually get approved. This is related with the cases that IU is interfered. False negatives refers to the scenario that an SU should be approved but finally get denied. This is related with the loss of spectrum utilization. So the evaluation result shows that false positive rate is 0 because of our quantization setting. Recall that we always quantize parameters to the humble direction. So the false negative rate is 2.72%, which is also very low. So next, I will evaluate the efficiency of P2-SAS compared with traditional SAS. In one spectrum access request, P2-SAS needs nearly 7 seconds to respond, and traditional SAS needs only 0.13 seconds. The communication overhead is 4 megabytes versus 6 kilobytes. So we can draw the conclusion that even if the P2-SAS is not as efficient as the traditional SAS, it is because of the privacy-preserving feature, but it is already good enough for real-world deployment. So if you are interested in the paper, please read it. You will find more details like formal security definition proof, security computation of the tricky parts, and so forth. That's it. Thank you very much.